Hi everyone and welcome to my YouTube channel. So we're continuing our inequalities playlist. In this video we're going to discuss a new inequality. So far we have discussed basically just two inequalities. The first one was the AMGM and the second one was the Muirhead's inequality. And in this video we're going to discuss a new one, which is the Cauchy inequality. So I hope you guys are excited. What are we waiting for? Let's get started. Alright, let's start by writing the Cauchy-Schwarz inequality statement. So first of all, we're going to write the main statement. Usually, we just say Cauchy's inequality, but it's basically Cauchy-Schwarz. Okay, so let's say we have two sequences of real numbers. So we've got a1, a2 till an, and we also have b1, b2 till bn, and these are just some real numbers. They're just real numbers, so they don't have to be necessarily positive or non-negative like the AMGM. So this is a good advantage for Cauchy's inequality. Okay, so what exactly is the statement? So the statement is the following. We can, okay, first of all I'm going to write it without the sigma notation. So a1 square plus a2 square and so on till an square. This one times b1 square plus b2 square and so on till bn square. This thing is actually greater than or equal to a1 b1 plus a2 b2 and so on till an bn. Of course, all of it squared. Okay, so if you take a look at it, of course you can see that the inequality is homogeneous, because you can see degree 2, and here degree 2 squared, so it's degree 4. And basically, as we said, they are just real numbers, so they don't have to be necessarily non-negative. And the nice thing is that, as you can see, we have, like here, one sequence, sum of squares and sum of squares, and then we find that we suddenly like mix them. So a1, you can imagine it as a1 square times b1 square. We multiply these numbers, and then we take, the roots of that, so we get a1 b1. The same thing here, this times this, then we take the roots and we get this thing. So of course, if you want, you can write it without the squares, but then you're going to have, here roots and so on. So basically this is the Cauchy's inequality, and of course if you want to prove it, then it's really easy. It's not difficult to prove. You can simply expand this, the LHS, and expand the RHS. You will see that a1 square b1 square, and here we're going to get also sigma a1 square b1 square, so they will cancel. And here, of course, the remaining is, the 2 sigma a1 b1 a2 b2, this thing. And here you're going to get a1 square b2 square, and like the same thing, like here you have a1 square b2 square, and here you will also get a2 square b1 square. So you can easily see that you can actually prove it using AMGM. So if you just do like this plus this and apply the AMGM, you're just going to get 2 times this thing. So as you can see, you can easily show it or derive Cauchy from AMGM. Okay, so if we think about it, when exactly does the equality hold? If we are saying that it came from AMGM, is it just like AMGM when all the numbers are equal? So all of these guys are equal. Of course, you can check that if all of them are equal, then indeed we have equality. But in fact, there is a nice thing that's not necessary. The equality case, like it's not like the condition for the equality that we must have all of the numbers are equal. It's not like an if, like a double if, or like equivalent statement. So when exactly do we have equality? Remember, we said we can show it using AMGM. How did we apply AMGM? We did something like this. b2 square. We applied AMGM here on these two. So if this is equal to this, that means if a1 b2 is equal to a2 b1, you can rearrange this like this: a1 over b1 is equal to a2 over b2. And now you get that they are basically proportional, the two sequences. So of course here we got a1 over b1 is equal to a2 over b2, and similarly for the others, you're going to get that the equality case holds when all the sequence a1 is proportional with to b1. So basically this is the equality case. It's not like the AMGM when all of them are equal. In fact, here you've got lots of freedom for the equality case. And of course this is a kind of good and bad at the same time. The bad thing about it is that now equality case does not help us in deleting some bad applications of Cauchy. You remember AMGM, we said that the equality case helps us a lot. Here Cauchy unfortunately does not help us because the equality case can be super random. So even like if you're applying, we might get something like this. Like maybe, of course, if you're playing on these two sequences, like this is ABC, and the other sequence is 2B plus C, and the rest of the stuff, we can still have this. They are proportional if all the numbers are equal. Like if A equals B equals C, then we still have this is proportional. This is 1/3, this is 1/3. So you really can apply the Cauchy on some random sequences. Okay, so let's just write that. So the equality if we have a1 over b1 equal to a2 over b2 and so on till an over bn, you can say they are proportional. Of course here we are assuming that the denominator is not 0 for any one of them. Otherwise, like you can just say that ai is equal to lambda, some constant lambda, times bi. Okay, so this is basically the statement for Cauchy. Very good. Before we move on to solve some examples, we actually have a very important kind of a branch of Cauchy. It's basically derived from Cauchy, but it's really powerful in itself. This theorem is called the Titu's lemma, or the Engel form of Cauchy-Schwarz. Basically, it's derived from Cauchy, so it's kind of the same as Cauchy, but it has a kind of nice form, a unique form. So let's discuss that. So this is, as I told you, it has many names. In the USA, I think they call it Titu's lemma, but it has also other names. The Engel form of Cauchy. By the way, usually, like for abbreviation, we just say CS. If you say CS, then, or if you see it anywhere, they're saying by CS, then that means Cauchy. Okay, so what exactly is this? It simply says that if you have real numbers, also the same thing, these are real numbers, and you have also another sequence, but these are actually positive, then we have the following inequality: a1 square over b1 is a2 square over b2, and so on till an square over bn. This is actually equal, greater than or equal to the sum till an all square divided by b1 plus b2, the sum of the denominators, without squares, of course. And here we still have the equality case, like if they're proportional. Be careful, it's a1 to b1, a2 to b2, till an to bn. If these guys are proportional, then we have equality. Okay, how exactly is this derived from Cauchy? First of all, like you can see and appreciate the nice configuration of this. Look here. a1 squared, a2 squared, like you have some fractions, and suddenly you make them a single fraction, and you add all the numerators, and you have something squared, and here you also have the sum of the denominator. So it's really powerful, especially when you have something square in the numerator. So whenever you have squares in the numerators, then always think about Titu, especially with the fraction. So here, as you saw here, Cauchy, if you have something like polynomials like this, you can apply Cauchy. Titu is very nice for fractions, but actually we will see later that Cauchy is also very important for fractions as well. But anyway, how can we derive Tito's lemma? So actually it's really easy. Look here, you have the sigma b1, just bring it here. If you bring it here, now you're going to have two sequences, this sequence and this, each one of them. So now actually you can just do the same thing. So let's say you have here b1 plus b2 till bn. Then remember what we do. We multiply this one by this one, so the b1 will cancel, and we're going to take the root of this. So indeed you're going to get just a1, and you will add same thing. You're going to get a2, and so on, all of that squared. So as you can see, it's literally the same as Cauchy. In fact, many people don't want to write Tito's lemma or angel form, so they simply say that we multiply by sigma b1 and we apply Cauchy and we get this thing. And of course then they put the sigma b1 here. Okay, so simply that's it. So right now we have two powerful theorems, and we're ready to go ahead and start solving some practical examples. So let's start with our example 1. Okay, so we have 3 real numbers, and we need to show that 3 sigma a square is greater than sigma a all of that square. Of course, this is a really an easy question, but just to know how we're applying Cauchy. Okay, so one way to solve this one is simply expand. You're going to get sigma a square plus 2 sigma ab, and of course then you'll cancel one of them, and then you're just going to get sigma a square is greater than sigma ab, which is correct by AMGM. We already did that in lesson 1. However, our goal here is to solve it in another way. So how exactly can we use Cauchy here? So the nice thing about Cauchy is that here we already, if you look here, we're going to have sigma a square. So you have actually something like this. You have a sum of squares. And also the nice thing is that here you have the same shape as Cauchy, square, and here, as you can see, roots. So what actually you're missing is this sequence. But guess what? 3, this is actually a very common trick. You write 3 as 1 plus 1 plus 1. Whatever, you can put the squares or not. But basically, you can think about it now in Cauchy form. 1 square times a square, then you root it, so you get a. And the same thing for the other guys. So we're done basically. So this is just from Cauchy, and we're done. Okay, so this is just for you to know how we're applying Cauchy. Of course, don't expect something that easy to appear in math contests. Okay, right now let's do another example. Okay, now guess what? We're going to do our super standard, very common, most famous inequality in the world, which is Nisbet's inequality. As we said before, if you remember, we did this before in Muirhead's lesson. So we said that this inequality has tons of proofs, and you will see it nearly in all the inequalities we're going to discuss. So we're going just to do the standard Nisbet inequality. We're going to show this using whatever, either Cauchy or Titu. Let's see. So if you remember, to remind you, we have some positive numbers, and we need to prove that sigma a over b plus c is greater than or equal to 3 over 2. So how exactly can we do that now? if you remember, in Muirhead, the idea was super simple. You have fractions, no problem. Multiply, clear the denominators, multiply by, pi b plus c, expand everything, and apply Muirhead. You're done. Now, we want to do it in a much simpler way. We don't want to expand and do the boring stuff. So, how exactly can we do it immediately? As you can see here, we have a sum of a over b plus c. So, we've got fractions. So, what can we do? If you think about it, you can think about Titu, because you have fractions, right? But the problem is that the numerator, you don't have something squared. One idea that you might think of is you can make it like this, right? This is, some smart trick. I don't have a square, so I created a square in this shape, and now you can apply Titu like this, and now 2 sigma a. Unfortunately, this does not work, as this thing actually now gives you sigma a plus 2 sigma root ab, and this will not, give you stuff that are greater than sigma a. So this is a bad idea, and in fact, whenever most of the time when you get from something nice to something uglier, then here we did not have any root. Now you created a root. Okay, this is usually not a very good idea. Of course, we have some special cases, but okay, this is like not a good idea. So how exactly can we make this similar to Titu? Okay, remember Titu needs something square, see? Something squared. So what we can easily do is make a squared. How exactly? Easy. Multiply the numerator by a and the denominator by a. So now we have ab here and ac here. Now we're ready to apply Titu. Of course, now this is still the LHS. Now we can apply Titu. Sum a squared over 2 sigma ab. Now our goal is to show that this is greater than 3 over 2. Of course, the 2 will cancel with the 2. So now our only goal is just to show our inequality. You just need to show this 3 sigma ab. Of course, this one is really easy by AMGM. You can see that this is true. If you just expand this is sigma a squared plus 2 sigma ab. So this is just AMGM, and now we're done. Of course, you should always be careful. Right now, I'm not writing formal solutions, but when you want to write formal solutions, then you should not do something like this. Remember, this means equivalence, but this is not equivalent to our question because we applied some inequality here. So make sure you write it in a formal way. Of course, here we apply just Titu. Okay, very good. So what's the lesson learned here? The lesson learned is that we have this very famous trick for Tito's lemma. When you don't have a square in the numerator, create the square yourself. And how do we do that? Simple. Just multiply the numerator and denominator with the numerator, and you get something squared. Then you're ready to apply Titu, and then you're done. Okay. By the way, you can also prove this using Cauchy. If you hate to use Tito's lemma for some reason, then you can just do this. You can multiply this by, you need to remember to create the other sequence, and this sequence is going to have the b plus c in order, to clear the denominator, but this will not be enough because it's going to give you the root a, so that means you're going to need another a. So if you just do this, then by Cauchy, this is, sigma a squared, and now that means this thing is greater than sigma a squared divided by this. So you can also do this by just Cauchy and continue in the same manner. Anyway, like here actually Titu is more efficient in my opinion, but no problem. Okay, let's do our final example for today. So example number 3. So now we're given x, y, z are non-negative real numbers. So these are greater than or equal to 0, and we need to prove sigma square root 3x square plus xy is less than 2 sigma x. Okay. So the first thing you notice here is that the inequality is flipped. So here we're going, we want to maximize this, minimize this. This is, by the way, very important thing. In fact, many beginners in inequalities make this types of mistake. They don't focus on the greater or like on the sign of the inequality, so they end up doing something bad. For example, they start and they try to make this greater than or equal to something, and they see that they will never get this because you're going to prove exactly the opposite. So be careful, don't waste your time on something like that. Okay. Anyway, how can we maximize something like this? Okay, if you think about this, remember, we cannot maximize anything unless we have a product of two things, right? Remember, let's have a look at Cauchy. Here is Cauchy. So here you can see that A1, B1, we have a product, then a product. This sum of product, we were able to apply Cauchy in reverse here. You can simply say that this thing is less than the square root of these guys, square and square. So we want to also have the same thing. We want to have a product. So we want to factorize this. And the nice thing about Cauchy here, why we thought about Cauchy, is that we have a square root. And Cauchy, remember, if you apply it like this, the a and b are going to end up being squares. So this is very good. So let's just do that. How can we factorize this? Easy. You can clearly take x as a common factor. So that means the LHS is equal to sigma root x times root 3x plus y. Now we can apply Cauchy. Sigma x sigma 3x plus y, and don't forget the root. And this is equal to, of course, what is this? This is just 4 sigma x with sigma x. So this is actually just 2 sigma x, and now we're done. We got what we wanted. So as you can see, here we applied Cauchy in reverse. So like Cauchy in reverse is a great tool to maximize something like this. Sigma AB, you want to maximize it, apply Cauchy basically. It's very, very nice. Sigma AB is, you can always maximize it. Okay, and as I told you, the equality case really here is will not help you at all, because as you can see, we applied Cauchy on something that's like these two guys are not equal. Imagine you were doing AMGM, you will never do something like that, because this is very bad for AMGM. You are not respecting the equality case, since these two guys cannot be equal. So keep that in mind. Here in Cauchy, no problem. You can do whatever you want. The equality case usually is it will not put any limits on your application. Alright, so as a summary, today we learned the Cauchy-Schwarz inequality, the statement of it, and we saw that the equality case holds when the two sequences are proportional, unlike the AMGM. We also saw the Tito's lemma, or the angel form of Cauchy, which is just a branch of it. And this is a great tool when you have fractions and you have squares in the numerators. Of course, the equality is similar to Cauchy. We solved some examples. The first example was really simple, but just to keep this idea in your mind, you can always make 3 as a sum of 3 ones. And the second one was the standard Nisbet's inequality. And here, the very nice trick, very common. This trick is so important to keep in mind. How do we get Cauchy here? We simply don't have like a square thing in the numerator. So what you can easily do is multiply by a, both the numerator and denominator. And guess what? You got yourself a square in the numerator. So apply Titu, and now you're done. Finally, we saw that we can also apply Cauchy in reverse by simply, since this is kind of sigma AB, once you factorize it, it's like sigma AB. So you can just, apply Cauchy in reverse and you will get what you want. Especially that you're going to get rid of the square roots, the inside square roots. Of course, when you have like an outer square root, then it really doesn't matter. You can always get rid of it by squaring both sides. Alright, my friends, so that was it for today's video. In the next video, of course, we'll be continuing with more difficult and more tools or more techniques about Cauchy and Titu. In fact, in the next video, we'll be solving an IMO question. So don't forget to like, share, and subscribe to my channel, and see you guys in the next video.